We're still in chapter 6 now, so talking about normal probability distributions. In 6.3, we're going to talk about sampling distributions and estimators. Now, the key concepts for 6.3, we're going to consider the concept of a sampling distribution of a statistic. Now, remembering the definition of a population versus a sample. So the population could be a lot of data points that we're looking at. And when we're talking about a population, we're talking about parameters that describe that population. If instead we're not looking at every single data point in a population, rather we're looking at a sample of that population, then we're talking about the terminology of a statistic. So statistics describe a sample, parameters describe a population. This is a little bit of a review here. So in 6.3, instead of working with values from the original population, we're going to focus on the values of statistics, such as a sample proportion or a sample mean, and we'll get into what these mean. Where these sample proportions or sample means were collected from a sample of the population that we're actually interested in. Let's talk about some general behaviors of sampling distributions. So when samples of the same size are taken from the same population, then these following properties apply. Going back to this graphic here, if samples of the same size are taken from the same population, then the properties on the next slide apply. So property number 1, sample proportions tend to be normally distributed. We should know better what this means now after going through what we've gone through for chapter 6. Property number 2, the mean of sample proportions is the same as the population mean. We'll talk a lot more about this in the slides to come. Okay, next we're going to talk about sampling distributions of a statistic. Remember, statistics describe a sample, parameters describe a population. So right now, sampling distribution of a statistic, that touches on data from a sample, not a population. So to define this, a sampling distribution of a statistic, it's the distribution of all values of the statistic when all possible samples of the same size n are taken from the same population. Importantly here, this is when all possible samples of the same size n are taken from the same population. Now, as we go through 6.3, you'll see this. So the sampling distribution of a statistic is typically represented as a probability distribution in the format of a probability histogram, a formula, or a table. So we're going to apply what we know from chapter 6 so far on normal distributions. We're going to apply what we know about samples versus a population and how samples can be representative of a population. We're going to combine all that with probability distributions now. So we'll go through this, we'll do examples. Now, within the realm of sampling distributions of statistics, we have 3 main categories. The first category is sampling distribution of the sample proportion. So to define this, the sampling distribution of the sample proportion specifically is the distribution of sample proportions or the distribution of the variable p hat, with all samples having the same sample size n taken from the same population. I'm reading out these definitions, but we're going to go through examples of everything we talk about today. Here's the same bit of information now. So the sampling distribution of the sample proportion is typically represented as a probability distribution, either as a histogram, formula, or a table. Now, the second main category is the sampling distribution of the sample mean. So the first was the sample proportion, the second now is the sample mean. Now, to define this, the sampling distribution of the sample mean is the distribution of all possible sample means, or the distribution of the variable x bar that we've seen before. Again, with all samples having the same sample size n taken from that same population. Here's the same bullet point here, so we're going to represent this usually as a probability distribution. The third main category now, sampling distribution of the sample variance. So it's been sample proportion, sample mean, and sample variance. Keep in mind the general idea here. So if we have a large population, but we want to get parameters of that population, Instead of taking into account all of the data points in a population, we can instead just look at samples from that population. The idea here is to take samples from that population that are truly representative of the population itself. Let's define this one now. So the sampling distribution of the sample variance is the distribution of all sample variances, or in this case, our variable is S squared. Remember, S squared is the variance of the sample, where sigma squared is the variance of the population. So it's really important to keep that notation clear here, especially in this section. Again, with all samples having the same sample size n taken from that same population. The same information here again, we're typically going to represent a sample variance using probability distributions. Let's talk about some notation for the sample proportion. Here's the same definition again you've seen before. We're talking about sample proportion specifically. So we need to distinguish between a population proportion, or P, and some sample proportion. So how we do that is lowercase p in italics is the population proportion. For samples then, we have this notation of p hat. So lowercase p in italics with this hat over it. So p hat is for sample proportions, lowercase p is for population proportions. One tip here is that when symbols are used above a letter, as in X bar or P hat, they represent statistics. Remember, when we're talking about a sample, we use that term statistics. When we're talking about an entire population, we use the terminology of parameters. So far I've introduced sampling distribution of the sample proportion, the sample mean, and the sample variance. Let's talk about some behaviors of all three of these categories. So number one, the distribution of sample proportions and sample means tends to approximate a normal distribution. From the details in chapter 6, a normal distribution is going to be a bell-shaped curve. It's going to be symmetric. Behavior number 2 here relates to sample variances specifically. So behavior number 1 here was for sample proportions and sample means. Now behavior number 2 here, the distribution of sample variances tends to be skewed to the right. If you remember our discussion on histograms, skewed to the right means we have a data set that looks like this. So we have sort of a tail of data to the right, where the data is focused here more on the left-hand side, and then the tail skews to the right. So this is positively skewed or skewed to the right. Behavior number 3 here relates to sample proportions, sample means, and sample variances, so all three of these categories. This builds on what you know about samples and populations, where again, we want to select a sample so that it's truly representative of a population. So sample proportions, means, and variances, all three categories, all target the population proportion, the population mean, or the population variance respectively. In other words, the sample proportion targets the population proportion. The sample mean targets the population mean. The sample variance then targets the population variance. So building on this point now, while the proportions in each sample may not equal the proportions in the population, the mean of all sample proportions, remember sample proportions is represented by p hat, so the mean of all the sample proportions will equal to the population proportion. That's really saying that if we take enough sample proportions that represent the entire population, we take the mean of all of those sample proportions, we will actually get the population proportion. Similarly for means and variances, we have the same principle here. So in terms of samples, while the sample mean or X bar or the sample variance or S squared of one given sample may not equal that of the whole population. What is true though, if we take the mean of all the sample means there are, that mean will equal the true population mean or mu. Similarly, if we take the mean of all of the sample variances there are for a given population, the mean of all of those sample variances will equal the population variance, or sigma squared. One additional point here. So the expected value, remember what that is? That's the same thing as the mean. So the expected value of a sample statistic, whether it be proportion, mean, or variance, the expected value of those sample statistics is equal to the population parameters themselves. Keep in mind that the sample statistics can only equal the parameters of the whole population if we follow these guidelines and we end up taking the proportion of all the samples in a population, or the mean of all the samples in a population, or the variance of all the samples in a population. We'll go through a full example of each of these three categories. First, let's put these behaviors into a visualization. So let's visualize everything we've talked about so far. Let's start with category number 1, or sample proportions. So here, when we're talking about proportions specifically, our sampling procedure would involve randomly selecting n number of values to find the proportion then, or p hat, for each sample. Remember, p hat is for sample proportions, where p is for population proportions. So we sample all of these different samples in our population. All of these samples have to be of the same sample size n. So we'll take sample number 1, 2, 3, etc., however many samples we need. Then we calculate the sample proportions. Each sample will correlate with one sample proportion. So p hat 1 is for sample 1, p hat 2 is for sample 2, p hat 3 is for sample 3, and so on. If we take all of these individual sample proportions and we graph them, we're going to get a normal distribution. That is, we're going to get a distribution that's symmetric and it's bell-shaped. So let's go through the behaviors specifically that were on the last 2 slides. So number 1 is that I mentioned the distribution of sample proportions tends to approximate a normal distribution. That's seen here visually. So we took all these samples, we got each sample proportion, we plot those, we get a normal distribution from all of these p hat values, or all of these sample proportion values. Behavior number 3 is that sample proportions all target the value of the population proportion. That's true for proportions, means, and variances. In other words, while the proportions in each sample may not equal to the proportions of the population, what is true is that the mean of all of these sample proportions, or all these p hat values, will then equal the population proportion. Importantly, we have to take the mean of all of the sample proportions that we have in our population. So then additionally, the expected value, or the mean, right, that's the same thing. If you need to, I'd go back and review this meaning of expected value. So the expected value of the sample statistic is equal to the population parameter then. Let me say that again. We're going to take the sample proportions, or all these p hat values, for different samples that make up our population. If we take the mean, or in other words, we're finding the expected value of all of these sample statistics, or all of these sample proportions, then we will truly get a value that represents our entire population. In this case, we're using sample, or p hat values, to then get our population proportion, which is represented by just lowercase p. Let's talk through the same thing now for the second category, so sample means. Behavior number 1 is that the distribution of sample means tends to approximate a normal distribution. Looking at a very similar visual as we did for proportions, you can see that for a distribution of sample means, or all these x bar values, does look like a normal distribution. To set the stage here for means specifically, we're going to do the same thing we did for proportions, where we take samples from a population, we get the mean of each sample. Sample means are represented by the notation of x bar. Once we take all of these sample means, or all these x bar values, and we plot them, we're going to get a normal distribution. It's bell-shaped, it's symmetrical. Keeping in mind the notation here, so sample means are x bar, population mean is mu. Behavior number 3, it's the same thing for the 3 categories, where the sample means all target the value of the population mean. In other words, while the mean or X bar of each given sample, it may not equal that of the whole population. It probably won't. But the mean of all of the sample means will equal the population mean, or mu. In other words, the expected value, or the mean of all the sample means of the sample statistics, or X bar values, is equal to the population parameter. So importantly, we're choosing samples of the same sample size n from a given population. We're taking the mean of all these individual samples, or getting these X bar values. If we do this for all the samples in a given population, we get these X bar values. If we take the mean of all these X bar values, then that is going to be equal to the true population mean. Let's talk through the third category now. So sample variances, we see this image now. Notice that this no longer looks like a normal distribution because it's skewed to the right. It's not symmetric. It's sort of bell-shaped, but not really. So behavior number 2 is that the distribution of sample variances, the category we're talking about now, tends to be skewed to the right, as seen here. Behavior number 3 will look familiar because all sample variances target the value of the population variance. So remember our notation here. For sample variances, it's lowercase s squared, whereas for the population variance, it's lowercase sigma squared. So while the variance, or s squared, of each given sample from a population may not equal to the population variance itself, what is true is that if we take the mean of all of the sample variances, that will be equal to the population variance, or sigma squared. So again, in other words, we take the expected value of the sample statistic. Here, the sample statistic is getting all the variances of the samples in a population. Specifically, we're getting the variances of all of the samples in a population. So once we have all the variances from all the samples in a population, we take the mean of all these variances, then we're going to get our population parameter, or our population variance. Okay, so we talked about sample proportions, sample means, and sample variances. The goal is for all of these sampling procedures to then truly represent our entire population. Let's go through each of the 3 categories and do an example now. So here we're going to do an example of sampling distribution of the sample proportion, so the first category. Consider repeating this process. Roll a die 5 times and find the proportion of odd numbers. On a typical standard die, the odd numbers are 1 or 3 or 5. What do we know about the behavior of all sample proportions that are generated as this process continues indefinitely? So for this example, we're looking at sample proportions specifically. It's in the question itself. So we need to keep in mind what we know about sample proportions. You can go back a few slides and look at those behaviors for sample proportions specifically. So when we're looking at proportions, we have an entire population. We take all the samples of the same size n from that population. Some examples of proportions we could get by doing this, they're all p hat values, right? Some sample proportions then could be 0.2, 0.4, or 0.8. So we have all these individual sample proportions, then we can get an idea of what the population proportion is. So this figure illustrates a process of rolling a die 5 times and finding the proportion of odd numbers. I want to point out here how these sample proportions came to be 0.2, 0.4, or 0.8. How could we get that from this question? Well, for example, a proportion of 0.4 means we rolled the die 5 times. In 2 of those 5 times, we got an odd number. So we got this proportion value of 0.4 by taking 2 times of getting an odd number out of the 5 times we rolled the die. So that's 0.4. To get the sample proportion of 0.2 then, we'd roll the die 5 times and get an odd number only once. So you can imagine doing this 5 times, rolling the die 5 times over and over and over again. We're going to get different sample proportions each time. So we're told we're going to repeat this indefinitely. We're going to keep rolling the die 5 times and collect the proportion value, or calculate the proportion value. So in this part of the figure, it shows the results from repeating this process 10,000 times. But the true sampling distribution, so what we're looking at in 6.3 are these sampling distributions. The true sampling distribution of the sample proportion involves repeating this process actually indefinitely. So an infinity number of times. Here we're just looking at this process repeated just 10,000 times. That's it. So an important behavior of proportions specifically is that this data here will look like a normal distribution. This data here is all of the p-hats plotted for 10,000 times of rolling the die 5 times. Now we should repeat this indefinitely, an infinity number of times. Here we only have data for 10,000 times. But it's clear from this graph so far that between 0.4 and 0.6, those two proportions, the mean for the entire population is going to be 0.5, so in between those two proportions. We can also make this conclusion because the values of 1, 2, 3, 4, 5, and 6 on a die are all equally likely to occur. So thinking critically about this and what we know about a die, the proportion of odd numbers in the population is 0.5 because we know to find the proportion of rolling an odd number on a die is really equal to the probability of rolling a 1 or a 3 or a 5. So we're using the addition rule here. We have plus signs. We're adding these all together. The probability of getting a 1 is 1 out of 6. Similarly, the probability of rolling a 3 is going to be 1 out of 6. Same for rolling a 5. We have 6 different numbers on the die. So 1 6 plus 1 6 plus 1 6, that's 1/2 or 3/6. That's the same thing as 0.5. So to summarize for proportions, we have an entire population. We've done this an infinity number of times. Our sample size here is that we're rolling the die 5 times. So each sample 1, 2, and 3, that's all reflective of rolling the die 5 times each time. From each of those individual samples, we're going to get a proportion or a p-hat value. Theoretically, we're repeating this an indefinite number of times. Then, with each of these individual sample proportions or p-hat values, we take the mean of all of these sample proportions to get the true proportion value of our population. Here, during this 10,000 times, we can get a population proportion of 0.5. We can also think through this rationally and see that 0.5 does make sense. We're getting the true population proportion when rolling a die 5 times and finding the proportion of the numbers that are odd, or 1, 3, and 5. So that was sample proportions. Let's also talk about sample means. Let's consider repeating this process. So roll a die 5 times to randomly select 5 values from a population. Our population on a die is either 1, 2, 3, 4, 5, 6. Then after rolling the die 5 times, getting 5 different values from 1, 2, 3, 4, 5, or 6, then find the mean or X bar of that result. So we're going to roll the die 5 times. We're going to get 5 numbers each time we do that. We're going to take the mean or X bar of all 5 of those numbers. That's 1 X bar, that's 1 sample. We're going to repeat this over and over and over again to get all these different X bars or all these different sample means. So we'll ask again, what do we know about the behavior of all sample means that are generated as this process continues on indefinitely? So setting the stage here for sample means, if we have 10,000 trials again. So our sampling procedure here is that we're rolling the die 5 times. We're taking the mean or X bar of those numbers when we roll the die 5 times. Let's say for sample number 1, so rolling the die 5 times, we get a sample mean of 3.4. If we roll the die 5 more times, that's sample 2, we have a mean of 4.4. We roll the die 5 more times, that's sample 3, that mean is 2.8. Remembering our terminology here, X bar is the sample mean, mu is the population mean. So again, this figure illustrates a process of rolling a die 5 times, finding the mean of the results. For theoretical samples of 1, 2, and 3, we might get mean values of 3.4, 4.4, 2.8, and etc. for all the samples that we do this on. And we're doing this indefinitely. So I'll show you the distribution on the right-hand side on the next slide. It's the result of repeating this process 10,000 times. So that's with 10,000 different samples. So that's really rolling the die 50,000 different times, right? Because it's 5 times per sample. So although the figure shows us doing this 10,000 times, we should really be thinking about doing this indefinitely, so an infinity number of times. To hopefully be extra clear here, I'm going to talk through this slide now. So from the sample proportions, we have means of 3.4, 4.4, 2.8, etc. through an indefinite number of times, because that's what we're asked to do in the question, is to think about repeating this an indefinite number of times. So each of these numbers, each of these X bar values represents one sample mean. What is the population mean? How can we figure that out? We can also ask, are the sample and population mean the same? Well, maybe, but also maybe not. So the answer we get for a sample mean will always target the population of the mean, but it may not be spot on. So in the figure, we're doing this 10,000 times. We're getting 10,000 different sample means. That means we're repeating this process of rolling the dice 5 times, 10,000 different times, and getting a mean for each of those 10,000 different times. Now, based on sampling distributions, what we're covering in 6.3, I would expect to not get the population mean each time I take a sample mean. Nor would I expect to get the same sample mean for each of my different samples. But when I average all of these answers together, or I get my expected value, then I'm getting my population mean in the end. I'm taking all of these samples, I'm finding the mean, and taking the mean of all of those sample means to then find my population mean. So let me show you that last part of the figure here. So when I repeat this 10,000 times, I'm going to get a normal distribution that looks like this. Keep in mind those behaviors. So I'll get a normal distribution for a sample proportion and a sample mean. But remember, it looks a little bit different for sample variance. So when we repeat this 10,000 times, we get a normal distribution that looks like this. If we take the mean of all of these sample means from 10,000 times, we would get a population mean, or mu, of 3.5. It's important here to recognize again that the values of 1, 2, 3, 4, 5, and 6, they're all equally likely to occur. So therefore, we can make this conclusion that the population mean, or mu, is 3.5. We get this information by repeating this 10,000 times. We get this same information from repeating this indefinitely. It's going to be even more accurate when we repeat this indefinitely. Now, we could also reason through this. Even though we're only rolling the die 5 times, we could take the mean of all of our numbers on a die, so 1, 2, 3, 4, 5, 6. Regardless of rolling the die 5 times, or 6 times, or 4 times, or 3 times, or more, if we take the mean of all of our possible numbers on a die, we'll get 3.5. So this population mean does make sense. So thinking critically about the situation at hand, about the question, this mean of 3.5 does make sense when thinking through it this way. So again, if this process is continued indefinitely, on and on and on again, the mean of the sample means will be 3.5. Also, again, to mention, for sample means, they're approximately a normal distribution. Now, that won't be the case for sample variances, and we'll look at that next. So far we've had a scenario where we had a whole population. We wanted to find the sample proportions to then get the population proportion. We also had a whole population of data. We found the sample means in order then to get the population mean. Another possibility is that we have a whole population of data. We take samples of that population and we find the sample variances. Then we take those sample variances and we get information about the population variance. Here's a reminder of what the formulas for population standard deviation and population variance look like. Remember, these formulas for a population are different than the formulas for a sample. So for a population standard deviation, we have sigma is equal to the square root of everything inside here. Population variance is sigma squared. So remember, for population, it's in terms of sigma. For samples, it's in terms of lowercase s. Where the population variance is sigma squared, it's equal to the summation of x minus mu, all of that squared, over n. Where x is each data point in a population, n is the total number of data points in that population. Let's do this example now using sample variances. So consider repeating the process that we've talked about before. We're going to roll a die 5 times, find the variance, or s squared, of each of those samples, where each sample reflects rolling the die 5 times. What do we know about the behavior of all sample variances that are generated as this process continues on indefinitely? So here's our figure now. We have a whole population. We're taking samples of the same size n from that population. We're finding the sample variance, or s squared, of each of these samples. Then with each of these s squared values, or sample variance values, we're taking the mean. When we take the mean of all the sample variance values, we get the population variance, or sigma squared. Now, unlike sample proportions and unlike sample means, sample variances don't tend to lead to a normal distribution. So as mentioned, this figure illustrates the process of rolling a die 5 times and finding the variance of each of the results, or each of the samples. Examples of sample variances: 1.8, 2.3, 2.2, etc., for all the samples in your population. So this figure results from repeating this process 10,000 times. Really what the question is asking is that we repeat this indefinitely. So because the values of 1, 2, 3, 4, 5, 6 on a die are all equally likely to occur, and given what we see here in this visual, so we're taking all the sample variances, we take the mean of all those sample variances, then we get a population variance, or sigma squared, of 2.9. If this process were repeated indefinitely, many, many times, then the mean of the sample variances, aka the population variance, will be 2.9. Also, again, it's important to point out, for sample variances, the distribution of those sample variances is a skewed distribution. It's not a normal bell-shaped symmetric curve. Just a refresher here on the skewedness. So what is it meant to be skewed to the right? Well, data skewed to the right, or positively skewed, has a longer tail on the right-hand side of the histogram. This brings me back to a point that was made earlier. So remember, for these sampling distributions, I mentioned they would be commonly represented as probability distributions. Here's an example of how we represent this as a probability distribution. So we have frequency on the y-axis and sample variances on the x-axis. So this probability distribution is represented by a histogram. Remember, we can also represent probability distributions as a formula and as a table. A couple more points here related to 6.3, so estimators versus unbiased estimators. Let's define both of these. An estimator is a statistic used to infer or estimate the value of a population parameter. So it's good to have these estimators because a population can sometimes be really large, and we know we would like to use samples to represent that population. So here's the terminology for that. An estimator is a statistic, so remember, statistics relate to samples, used to infer or estimate the value from an entire population parameter. In statistics, we always want to try to be as unbiased as possible. So an unbiased estimator, it's a statistic that targets the value of the corresponding population parameter in the sense that the sampling distribution of a statistic has a mean that is equal to the corresponding population parameter. So this should sound familiar because those 3 categories we just went through, those are all examples of unbiased estimators. So remember, for statistics, they're not parameters because statistics reflect samples. So the statistics we just talked about, they're considered unbiased estimators. That is, they each target the value of the corresponding population parameter, where the sampling distribution has a mean equal to the population parameter. Again, this should sound really familiar because these are the three examples we've been talking about so far in the lecture. So, to be clear, unbiased estimators, examples of these are proportion or p hat, mean or x bar, and variance or s squared. These are all unbiased estimators because they describe a sample that can then be reflective of a whole population in an unbiased fashion. Now, these are counter to biased estimators. So I'll talk through examples of biased estimators. That is, they do not target the value of the corresponding population parameter. So for the median, the range, and the standard deviation, if we have any one of these statistics, it doesn't really help us infer information about our whole population. Why not? Well, because these are usually biased. So remember, the median is the middle value of the data set. So knowing sample medians won't really help us with a population median. Again, for the range, it's the maximum data value minus the minimum data value. If we know the range of a whole lot of samples that make up our population, it's not going to tell us about the population range itself. Similarly, for standard deviation, if we know the standard deviation values of all these samples of our population, the standard deviation value is going to be a biased estimator of the whole population. So remember, to be unbiased, we want to take the proportion, the mean, or the variance of samples of our population. Then we could take the mean of all the sample proportions, the mean of all of the sample means, or the mean of all the sample variances, and get corresponding population parameters that are truly reflective of the population. One last slide here that's a refresher on what you've seen before when dealing with or without replacement. So we talked about it being easier to work with samples where we do have replacement. So we take some sample out of a hat or a jar, for example, we put that marble back, and then we pull a sample again. When we have a sampling method that's with replacement, then the denominator stays the same each time. For instance, if we have 6 marbles, I pull out 1 marble. I had 1 in 6 chance of pulling out that same marble. If I don't replace that, then I have 5 marbles remaining. Then I have a 1 in 5 chance of selecting the next marble. Instead, if I'm doing sampling with replacement, then my denominator stays the same. It's 1 in 6 for the first marble. It's still 1 in 6 for the second marble, and so on. So coming back to this slide, sampling is conducted with replacement because, number one, when selecting a relatively small sample from a large population, it makes no significant difference whether we sample with replacement or without replacement. Again, this holds true when we're dealing with a large population and we're taking a relatively small sample from that population. Number two, sampling with replacement results in independent events. Independent events are unaffected by previous outcomes. As I mentioned with that marble example, independent events are easier to analyze and result in simpler calculations and formulas. For that example I just talked about, we didn't have to change the value of the denominator each time if we're doing sampling with replacement. Okay, so to summarize 6.3, we looked at sampling distributions. Specifically, we looked at sample proportions, sample means, and sample variances. Using the unbiased estimators of proportion, mean, and variance, we could take information from all the samples of a population to get information about our population. This is the end of 6.3. I will see you next time for 6.4. As always, never hesitate to reach out if you have any questions about anything. I'll talk to you soon.